Okay, we're back. Hopefully the camera is a little bit more stable now. So let me just remind you about the meaning of the expectation value. So the expectation value of any operator, if I have, say, a generic operator, A hat, the expectation value of A hat is equal to the average of many measurements of A hat, whatever that represents. Maybe it's the energy, maybe it's the momentum, on initially identical systems. And we could write in bracket notation, I could write that A hat is equal to the inner product of psi A hat psi. Or to compute that, I would take the integral over all space of psi star A hat psi, d cubed r. So the particular thing that we're trying to find right now is the expectation value of the energy, for which the relevant operator is the Hamiltonian for the whole crystal, which is the kinetic energy term minus h bar squared over 2m del squared plus the potential energy term. So this potential energy includes the interaction of the electron with all the infinite number of nuclei, or at least a very large number of nuclei in our system. So we're going to take our tight binding wave function and plug it into this expression for the expectation value using the Hamiltonian. And so when we do that, we get that the expectation value of the energy in the tight binding state would be, there are two factors of psi that appear here. Each of them has a 1 over root NL, so combining those I'm going to get 1 over NL times the integral over all space of, I've got to have my two different psi's here, so that each one of them has a sum in it, so I can write the first one as a sum over j e to the minus I k dot tj, minus sign because the first psi, we're taking the complex conjugate, times the atomic wave function, complex conjugate phi star, centered on the lattice point tj. So phi star with its argument being r minus tj, times the Hamiltonian, and now I need a second, the Hamiltonian operating on psi. I need a second sum, but I can't use the same sum index as this one. I need to use a different sum index. So I'll call this one j prime, e to the I k dot tj prime phi of r minus tj prime d cubed r. So let me just shift this up a little bit and we can continue on to the next page. So I can now take advantage of the fact that an integral is just a different type of sum, and if I have different sums, I can commute the order, and so I could rewrite this as, move this paper down a little bit, fix this up. Okay, good. So I can rewrite this as the expectation value of E is equal to 1 over NL times the summation on J times the summation on J prime of the integral over all space of e to the minus I k dot tj phi star of r minus tj, Hamiltonian operating on e to the plus I k dot tj prime, phi of r minus tj prime d cubed r. Now, for each one of the terms in this phi j prime summation, we're summing over all of the other lattice points, all of the lattice points j. And since all the lattice points are identical, the result of doing the sum on j for every different term in the sum on j prime is going to be the same. So that means that we can replace this sum on j prime just by multiplying by the number of lattice sites. And so that's going to give us, replacing this sum by n sub l is going to cancel with that n sub l there. And so I'm going to wind up then with that the expectation value of the energy is just the summation on j times the integral over all space of e to the minus I k dot tj phi star of r minus tj Hamiltonian. And instead of all this, remember, as I was just saying, the result, because you're summing over all lattice points here, the result that you get, and because all those lattice points are identical, the result that you get for any value of j prime is going to be the same as for any other value. So we might as well pick the one that's the easiest, which is I'm going to choose tj prime equals 0 for this particular sum as a representative member of that sum. So when tj prime equals 0, sorry, this exponential just gives me 1, and I'm left just with phi of r d cubed r. Okay, so far this is the only approximation that we made was back when we assumed our tight binding wave function. But this is still a complicated calculation to make, and so we're now going to make an additional approximation to simplify things. So I'm going to see if I can do something about that noise, so we'll be back in a minute.